All right, great. So my name's Stephan. I'm from a team of scientists at Google, and I'm going to tell you about some work I've done today with a bunch of colleagues from Google and a few from Harvard. Okay, so I'm interested. Oops, a little fast. So I'm interested in how machine learning can improve really sort of complex, sophisticated scientific computing. So things like maybe like a numerical weather forecast or designing an airplane. And so I think that these sort of simulations are actually rather remarkable. They sort of incorporate sort of huge amounts of our sort of prior knowledge of the sort of physics, how the world works, huge amounts of data. They often run on really big computers. So this is basically what we use supercomputers for. And they're actually often very complex. So in many cases, hundreds of thousands or even millions of lines of code. So I don't think I have the answer for sort of all these questions, but maybe a few ideas that may be relevant. And so I wanted to start by talking about the way I think that we're not going to solve scientific computing with machine learning. And that we're not going to solve it by just throwing out everything we know about scientific computing and replacing it with black box machine learning. And so this is one example of a recent paper that I like, where someone tried doing this for weather forecasting. A few folks at the University of Washington and Microsoft. So in this study, basically they tried to they I guess made it a respectable effort at training some sort of black box deep learning algorithms, things like convolutional LSTMs, or kind of the sort of the sensible things you would try in your deep learning toolbox. If all you know is that you know that there's some sort of translation symmetries essentially, and when you do that, you end up with a weather forecast that I guess the error is about halfway between these simple baselines and sort of maybe a numerical weather forecast model. But this is actually really bad. This is probably equivalent to going back in time to really the early dawn of weather forecasting. Maybe I don't know, maybe like a 1960 or 1970 era weather forecast. Probably something you could do on your graphing calculator. So why? So I guess this paper doesn't go into exactly why the algorithms didn't work here, but I think a lot of people have tried this sort of thing now, and we can suspect there's something about these. One answer might be that the physics-based model is doing a lot more computation. So these weather models are run on supercomputers. As another answer is that the physics-based models are actually incorporating a lot of huge amounts of our domain knowledge about how the world works, and sort of lots of knowledge of of laws of physics as well. And the deep learning models have to learn that from scratch, which is really not. But we know sort of the equations that we're actually solving. So I think that maybe there is a way that deep learning is relevant, and that's this concept that's been emerging recently, known as differentiable programming. And so I've traced it back to, as far as I can tell, sort of the first sort of a few of the better sources on this are actually, there's a Facebook post and a blog post from Andre Carpathy and Jan LeCun talking about this notion of differential programming. Andre called it software 2.0, and here it's sort of thinking about deep learning not as just another form of machine learning, but as a way of writing parametric software programs, where you can express that allow you to sort of express some much larger class of computer programs that maybe you could easily write down by hand, in a way that we can optimize the computer programs. So it's not quite sort of fully writing software, but it's sort of parameterized software that we can optimize. That's right. So parameterized, automatic. A sort of a key ingredient here is that we have a training procedure that lets us do this. So we have automatic differentiation, and we know we can optimize these programs with gradient descent. And this is maybe roughly speaking sort of the recipe that explains how deep learning works so well, is that we can easily customize it to new problems. You can adjust the architecture. You can swap in a new loss function. You can even sort of add in entirely entire components that don't look like a normal deep learning module. So we can even add in sort of fixed components of programs along with sort of the parameterized flexible neural networks. So I think that for scientific computing, I think differentiable programming is really exciting because it lets us combine the best of both worlds in terms of using machine learning for solving approximation problems and using sort of known physics for sort of imposing physical constraints. And particularly, we can use sort of well-established numerical methods for solving equations in order to sort of to add that prior knowledge. So that gives us aspects that gives us some interpretability into our programs, and also hopefully some level of generalization. Because as Nathan said the other day, so neural networks really, I don't think there are any good examples of machine learning doing anything other than interpolation. So if we want to solve complex problems, we have to figure out how to transform them into interpolation problems. And that's where I think differentiable programming comes in, because sort of adding more physical knowledge to our problems. So for example, one example of an equation that is sort of never violated in these weather simulations is the continuity equation. Basically says the amount of stuff in a box is, you can calculate it from adding in stuff that goes in and out of one of the walls. This equation is relatively easy to sort of impose by constraint. For example, if we're solving PDE, use a finite volume formalism. This is the sort of thing that we want to be able to put into our machine learning models, and we don't want to have to learn, because machine learning models they struggle to learn really firm rules. Even if we satisfy this equation to, say, a loss of, I don't know, 1 part in a million or a billion, if you run that model sort of on itself a whole bunch of times, eventually that can cause your sort of violating sort of the physical laws may cause your model not to generalize very well. Okay, and so to do this, you need to know how to sort of differentiate numerical algorithms, and this is something that I think is sort of well known, but maybe not entirely widely known, is that we actually do know how to differentiate nearly anything you can write down with a computer, and that includes most algorithms we do. So that includes differentiating through physical constraints. So in most cases, when you're solving a physics problem, it's maybe a little different from how you'd write down a normal computer program, in the sense that so physics is really it's all about writing sort of equations and sort of constraints. And oftentimes we use pretty complex algorithms to solve equations. But sort of in a very generic sense, you have some parameters, and you have some function u here that gives you a solution. It's a function of the parameters, and maybe it's described by some sort of implicit equation. And so there's kind of one magic rule for calculating derivatives that I thought I'd mention, and it's sort of known as the adjoint method in sort of the physical sciences. Basically, it's just the total derivative on this equation. If you differentiate with respect to the u's and the m's, and you rearrange things, you end up with a large linear equation here called, this is the tangent or the adjoint equation. And so you can define just in terms of this function f. So this is a pretty neat trick. It means that we can actually differentiate through physics in many cases without knowing the details of how we obtain the solution. So you can use whatever complicated iterative method you want, for example, to solve for equations, and all you need to know is how to sort of differentiate at the solution. And this is used for, again, for fields like control or data assimilation, inverse problems. It's a lot easier when it's augmented with automatic differentiation. This is a tutorial that I found very, very helpful for helping me understand how this works. Okay, so today I want to talk about two examples of differentiable.
The implicit function theorem, right?
Implicit function theorem. Okay. Yes, I believe that. Yeah. I was not familiar with that name, but yeah, it's not. Yeah. So I want to talk today about two examples of differential programming for scientific computing in the context of partial differential equations. And so here, kind of I guess the premise again is sort of looking at how we can sort of take complex scientific programs. We don't want to throw out sort of our prior domain knowledge. We just want to sort of swap in a little bit of machine learning into the context of some sort of complex scientific program. So the first example is going to be looking inside putting machine learning sort of inside a big sort of physics numerical method for improving how we solve partial differential equations. And the second example is going to be looking at a case where we have a physics model, and we're going to feed some machine learning into the physics model, and we're going to sort of optimize the whole thing together as well. And specifically, I'm going to look at we're going to look at solving PDEs like some equations of fluid dynamics. And we're going to look into sort of optimization problems, things like structural optimization. So, for example, designing a bridge from first principles. Really, just say that you want to hold up some weight on here from some supports, and where should you put stuff in between? Okay. So first, I'm going to talk about learning discretizations for partial differential equations. This is some work we published in PNAS earlier this year. Okay, so this is, I don't know, some overview slide I have on PDEs. I'm sure most of you are familiar with PDEs, but again, PDEs I think most of the phenomena we see around us is a PDE. Everything that's continuous in physics is a PDE. They're really useful for lots of practical engineering and science applications, things like weather forecasting, things like aerodynamics, things like combustion. And of course, the equations are simple in many cases. In most cases, we know what they are. We just don't know how to solve them practically. We have to discretize them on computers. That's expensive. So more concretely, this is an example, coming back to weather forecasting. This is an example of a recent hurricane. And here's the sort of the satellite photo. Here's sort of the resolution of this PDE in a state-of-the-art weather model. And as you can see, in the state-of-the-art weather model, we actually have a very pixelated view of the world. And this is a global model. This is maybe a 10 or 20 kilometer resolution model here. And the challenge, of course, so a lot of this fine resolution detail here, which if you want to model how clouds work, you want to model convection properly, you really need to sort of be modeling like this fine detail and this fine variation. That's all washed out in the simulation. So instead, the simulations use a lot of sort of crude approximations for the subgrid physics. But if we really wanted to say study how the importance of clouds, and if we really wanted to sort of physically understand sort of like really how a hurricane works, or we wanted to say make predictions about the impacts of climate change, we really would love to be able to sort of simulate this at effectively much higher resolution. Of course, if you want 10 times the resolution, say to resolve clouds, you end up actually needing about 10,000 times the computing power. That's because you need scale in 3 dimensions plus time. So that's probably not feasible because we're already running this on many of the world's biggest supercomputers, and Moore's law is kind of slowing down. And even if it wasn't slowing down, that's still like decades in the future. Okay, so coarse graining is an important problem for PDEs. What does this usually look like? Well, so in principle, you have some sort of PDE here. I'm showing this is the advection equation, which is kind of like basically the simplest equation of fluid motion. And you have some very nice high-resolution picture. But you can also imagine coarse graining it. If you do it exactly, just say sort of pixelize everything, and you can imagine that there's actually, at least by eye, I kind of see these blobs moving around. So it seems plausible, perhaps, that you can kind of trace out their evolution. Now, if you could do this with exactly the same method, and you did it, say, on 4 times coarser of a grid, that's in 3D, that's 250 times faster. So that's kind of the appeal here, is that you could coarse grain things and potentially have methods, and they use much less memory, and they're also much faster. And that's, of course, when you actually do this, with sort of standard numerical methods, it breaks, and that's because we sort of have broken the assumptions that the numerical methods are based on, which is that these equations are smooth and continuous. And so you kind of have a choice maybe of sort of either you say here that this is standard finite volume method, you get you very quickly get these sort of crazy oscillations that build up and just kind of explode after just a few time steps. Or you can use there's loads of tricks that have been developed for sort of stably solving PDEs, things like upwinding, slope limiting, flux limiting, and so forth. And that works too. But basically, what that means instead is that everything gets really blurred out to avoid to avoid these oscillations. What you maybe would like instead is something that picks some optimal level of limiting, so it still looks sharp, but never gets sort of too sharp, and that's pretty hard to do with standard numerical methods. So the question is if we can do better than these with machine learning. Okay, so the inspiration for this work, why we thought perhaps this is possible, comes from a field of machine learning known as super resolution. So in super resolution, the task is to take a blurry, maybe pixelated image and try to restore the detail, restore the high resolution detail. So this is a sort of an ill-posed problem here, but we do have some understanding of what a face should look like, so perhaps this is possible. Now, sort of one standard way to do this, I think sort of really, roughly not too far from the state of the art for many years, was to use something like a bicubic interpolation. So really just say like fit some simple curves, and you can get rid of the pixelated nature very easily, but you still end up with the face that looks really blurry. This is obviously not a face. Oops. This goes really fast. So we can do it. So recently, I think, especially over the past few years, we've seen that we can do that we can use sort of neural networks, machine learning, to do a really nice job of sort of resolving details with in cases like this. So here, this neural network has sort of reconstructed a lot of detail. This looks a lot more like. Here, this looks a lot more like a real, well, it's a cartoon face, but it's at least looks like something that might be plausible. It still misses some of the detail. If you compare to the original, the fine structure here is off, right? Like here in like the necklace, for example, doesn't look quite right. But it looks pretty good, a lot better than like this bicubic interpolation. This is from a group at Twitter. This is actually, I guess, 3 years ago now. So undoubtedly the state-of-the-art methods have moved on past here significantly. But this is the sort of thing we'd like to imagine doing with on our PDEs, particularly. Oh my goodness. Particularly if you look at something. If you look at the numerical methods we use for solving PDEs, most of them look a lot more like this bicubic interpolation than this neural net. So can we take this sort of idea and port it to PDEs? So let me walk you through what it's like to solve a PDE. So with a PDE, we imagine that we're modeling some sort of continuous function here. We're doing it in 1D. We want to sort of evolve determine how this curve is going to evolve over time. Now to solve it on a computer, we have to discretize it. We choose some points. That's what's happening here. So we'll pick 5 points for each of these curves. Now we pretend that we don't. Now we don't. Goodness, maybe we'll just use the slow but steady. All right, sorry. Okay. We choose our grid points. Now we pretend we don't know where the line is, and we just have access to the discretization. Now we need to figure out how to advance to the next time step. To do that, we basically have to plug into our original PDE. And to do that, we need access. The hard part is that our equations in PDEs depend not only on function values, but also on function derivatives over space. And doing that is hard. We have to say, what is the slope of the curve at each of these red points when we don't have access to it. So you need a model for that. And so one classic way to do that is is polynomial interpolation. And this is what's done in a finite difference scheme. It's not, and there are other versions as well, but basically this is a very standard sort of thing to do. The problem here, if you fit a, I guess it would be, you pick a polynomial through these 5 points, you get these extra oscillations. And that's because we didn't, so you end up sort of overshooting things. And this is a perfectly reasonable fit to 5 points if you didn't know anything about their structure, but of course we do. In particular, in this case, we're solving an equation called Berger's equation. We know a few things. We know what the formula is, though this may not help you very much if you haven't studied Berger's equation before. But even just empirically, we can solve this equation a bunch of times. Maybe we solve it with if we solve it with like a really fine grid, or and you can, in some cases you can do it analytically, and you can notice that the Berger's equation has some sort of characteristic structure. And it turns out Berger's equation tends to represent shock waves. So these are a bunch of examples of what Berger's equation looks like. It forms shock waves, and they're always going in one direction. So if you have this prior knowledge, I guess it should be no surprise you can train a machine learning method which basically gets this interpolation sort of perfect. It sort of exactly matches up to this curve. Okay. So this approximation here, this aspect, this estimating spatial derivatives for PDEs. This is perhaps sort of the main approximation that you need, and sort of almost everything else you can do exactly or sort of near exactly. So one way, for example, to solve a second derivative is to use an expression is to sort of do a linear reweighting of 3 points on a grid. This is if you can calculate a limit, you can prove that if you make delta x small, this converges. That's great. It's not the only way, of course. For example, you can also do a 5-point stencil as well. This version is instead of being a second order accurate in delta x, it's fourth order accurate. There's maybe no inherent reason why you might prefer one over the other. This one, I mean, which is going to be more accurate is going to depend on how smooth your function is that you're modeling. These are sort of 2 valid choices, but there's actually an infinite number of sort of valid choices that could also approximate spatial derivatives on a grid. So this is kind of the task that we're going to parameterize with a neural network. We're going to want to learn parameters here like these numbers -1, 16, 32, 16. -1 with neural nets that are going to sort of optimally pick the right form of the right coefficients for computing spatial derivatives. This is the only part. This is the only part of algorithm we want to place in machine learning. So our machine learning setup here again is we're going to run simulations at really high resolution to make training data. And we're going to do sort of a standard supervised learning to try to fit these parameters. And to solve things on very coarse grids. So grids that are so coarse that our standard numerical methods would just blow up. Okay. So our programs, our sort of differentiable programs, are going to look a lot like standard programs for solving PDEs. And there's a lot of boxes here, a lot of components that I'm not going to go through entirely, but this is a relatively standard finite volume method. It embeds a lot of domain knowledge about the PDEs. So for example, it knows the exact equation that you're solving, like the formula you'd write down for Berger's equation. Not the solution, but what the equation looks like at any given time step. It does things in terms of the flux, which lets us apply this continuity equation exactly. So we're going to get conservation of so we're going to say conservation of momentum here exactly. We're going to sort of writing things, of course, in terms of an ODE. So we're discretizing in terms of a set of ODEs. So we'll use in this case we use sort of explicit ODE solvers with sort of dynamic time stepping. And the only part we're going to replace with the neural network is one little part here, which are these coefficients that go into computing spatial derivatives. And here we're going to use a small little sort of a few layer neural network. With convolutions, which sort of embed our translation invariance. Okay, so we can train our neural network models to do this. Let me show you an example of what this looks like on Berger's equation. So this blue line is sort of this exact equation at really fine resolution. It's really hard to get these shock waves right with sort of the standard numerical methods. You have to use a lot of tricks. So one sort of very simple baseline here is if just fitting these polynomials, you get these extra. You see is these extra so near the shock fronts, you see these extra oscillations that go up and down. This is even on. I mean, if you wanted to sort of fully resolve things with these methods, you might need more like a few hundred points instead of 64 points. But our neural network can actually basically represent the function using basically just enough points to kind of see like the rough structure. This makes sense. I mean, like at least by eye, you can imagine sort of tracing out the. This is enough. These are enough, just barely enough points to kind of like reconstruct the shape of the function that you're solving. And if you've seen a lot of solutions of Burger's equation, then perhaps like that's enough to see how it evolves. Yeah.
So these red points on the right, those are solved without like constantly updating to the true solution. Like that's actually autonomous. Or? Yeah,
so I should note this equation there's a forcing term. So the forcing term is for this particular equation, the forcing does kind of force you. So the forcing does kind of force the solution back, like in terms of getting to in terms of even if you make like some large errors, the forcing is going to kind of restore things. Okay. That's not true for some of the other equations we looked at. But yes, this is running the neural network on top of itself a bunch of times. Yeah.
So you are training your network on a grid basically with only 16 points, right? So what happens if I take the network and I now put in 32 points? So if I change my discretization, do I have to retrain the whole network, or is there a way to?
So for this work, yes. When we solved it on a different grid, we did well, it depends on what you mean by 32 points. So if 32 points means
final discretization.
So just make it so finer discretization. In that case, we train different at every resolution. We train a different model. What does work, and I'll show you in a slide or two, is that you can make this grid bigger, sort of just like a larger space. And there, this discretization works fine. Yeah.
Yeah. So just to understand the output of the net, you're outputting the coefficients to the polynomials.
Yes.
Are you choosing those from an existing set of stencils for PDE solutions, or is it just saying, hey, give me like k coefficients?
So we really are like allowing for sort of very flexible coefficients like on these stencils. We can impose certain constraints on them. So for example, we impose that they're at least first order accurate, which turns out to be just an affine transformation.
And if you look at the coefficients, are they close to what you would get for like a 3-5 point stencil?
Sometimes. Let me show you. I have that in a slide or two, actually.
And a follow-up question, are they time dependent?
They are time dependent. So we're using different coefficients at every point in time and space here. So, which is a bit more than sort of I mean, some numerical methods use that, but a lot of them just use constants. Let me show you really briefly kind of some sort of high-level results here. This is what our neural net looks like. It has way better error, much coarser than these baseline methods. And here, even this is in comparison to a method called Wino, which is sort of a very very sophisticated numerical method, like specifically designed for tracking that has basically explicit tracking for discontinuities in equations. So it's really very well suited for solving things like Burger's equation. Okay, we did this also a bunch of other sort of classic 1D PDEs, sort of models for fluid dynamics. And again, we see this is a different metric, but in this one, it's up and to the right is good. And we're able to improve over baselines on each of these. I'm going to talk a little bit about sort of interpretability we get here, which is that because we impose our model structure, we can look at the predictions of our neural network, say, in terms of these coefficients at each point on a graph. So we're solving this. So we can plot out what these what the optimal coefficients look like. These look maybe a little bit like what you would. They don't look entirely outrageous, but they're definitely not quite what you would. They sort of have I don't know, like a bigger sort of, I guess, like these sort of down wings than you might sort of expect for sort of some standard coefficients. But you can't. They do seem to maybe have learned some physics. And so one thing you can do is you can look at whether these coefficients are biased to the left or sort of biased to the right. And you calculate kind of here we call it like a center of mass for the coefficients, and you notice this interesting trend, which is that it's anti-correlated here with the parameter we're solving, which corresponds to velocity. And so it turns out, I guess what we see here is that our coefficients, we didn't build it into our equations, but our coefficients are actually preferentially, they're sort of biased in the direction that sort of in the what's called the upwind direction, the direction that the flow is coming from. This is actually a principle that is very commonly used in solving these sorts of equations called upwinding, which is that if you want to figure out, say, what's coming towards you in a fluid, say you have like smoke coming towards you, you want to look in the direction that the smoke is coming from, and because that's sort of the direction of causality. If you look downwind, maybe that tells you a little bit about what's happening, but it's not as good as looking upwind. And so the equations seem to learn that here, and we can sort of see that they're doing something sort of reasonable. It's not entirely obvious what's going on inside the machine learning black box that's giving us these parameters, but at least we sort of understand how they're used.
Can I ask you a quick question?
Yeah.
So these stencils that you show are basically supposed to represent the space derivative, correct? Like the first and the second.
Yes.
They don't seem to.
Sorry, this is actually a zeroth derivative. This is just doing a reconstruction of the signal on each of the on the boundaries.
Okay.
So here it's really just it's just doing interpolation. It's not even. There were other coefficients we had that were of course say computing higher order derivatives in space.
Okay, so you're not learning the space discretization, because then I'm confused what you mean when you say we learned upwinding, because upwinding I would use for the space derivative.
Yeah. So here we. So this term is used in the space derivative, but we learned some coefficients. The extra derivative comes from the finite volume method. So the finite volume method basically gives you there's one derivative that we're going to do sort of exactly as just like a first order difference, and we're going to sort of apply that to this. We're going to sort of reconstruct the signal here, and then we square it because that's what's happened in the Berg's equation. Then we apply this finite volume difference.
Okay. Is it fair to say what you really are learning is the relation? It is the relation between a finite stencil and the actual derivatives at the center point, right?
Yes.
So somehow the idea is that the PDE lives on a relatively lower dimensional manifold, and what happens can be parameterized in terms of 8 numbers, 12 numbers. We use usually derivatives, but you don't use the derivative, you use the values on the stencil. So you are learning the derivatives of an actual PDE solution at the center point,
right,
as a function of the value.
Right. We don't have access to the exact derivatives of the PDE, so we're learning a way to approximate them.
So yeah. So what I'm trying to say is the following. In general, you can create a profile in the PDE that has the same 8 values, but is bananas at the center.
Yep.
So you're really learning some sort of, I like thinking of the words inertial manifold, but it doesn't particularly matter. That if the PDE solution lives on a low dimensional manifold, then if you have these values at 8 points, the derivatives at the center must be functions of these values, right? So there is something about the low dimensionality of the PDE behavior that sits under what the method is doing. Because in principle, you can take an initial condition for a PDE that you would have the same values at the 8 points, but would be completely crazy at the center.
Yeah, I agree. There's something inherently this PDE is actually much lower dimensional than say than even the number of points that we discretized it at here.
I think this is the thing that you are mostly extracting, this low dimensionality of the solutions of the PDE.
Thanks. Anything else? Yeah?
I have a very simple question. The neural network is trained from the high resolution
Yes.
solver to match each derivative.
Yes.
What is the loss?
So the loss. So we have a kind of a couple of types of losses, but either a loss based on sort of like the time derivative sort of at a single time point, or sort of unrolled over sort of multiple time steps as well. Mostly we found in this case that it was enough to not unroll over multiple time steps. Okay, and I guess one point here, this, in some sense at least, this extrapolates. We can train it on sort of a very small spatial domain, and then of course, and if you have sort of drawing from sort of a similar distribution, you can make a much bigger solution, and it extrapolates. And that's not too surprising because everything we were doing is just looking at sort of convolutions as some sort of local neighborhood. And as long as you see sort of everything, as long as we turn this whole problem into a sort of an interpolation problem, locally at least, our model should still work. Okay, and then I'll mention we're sort of working now in the direction of sort of scaling this up towards sort of 2D and 3D fluid mechanics. We're doing this on this advection equation where we see some where this is not in our paper, but it works pretty well in advection as well. And so I guess things are a little more complicated in higher dimensions, but there's kind of more reason to think that it should. I mean, these are obviously like all the real problems. Okay, so in summary, here this first example, we use machine learning to build better, at least in some ways, PDE solvers. We can use these physical constraints, so the differentiable programs give us some level of interpretability and generalization. We can beat some of these sort of hand-tuned methods. It's not necessarily much faster. I mean, actually, we're solving things on much coarser grids. But we're doing a lot more computation at each time point because we're like running inference of a neural net. Remarkably, it's actually about the performance is actually roughly comparable. And then part of that is because we're using the computation much more efficiently than how we solve PDEs normally. So normally PDEs are not tend to be memory bound, and that's not true when we're running a neural net. Okay, so I'm going to go through. Well, I don't know. I guess I have maybe 10 minutes to go through my second example here, which is all right. You can read the paper. So this is some work on that a few other colleagues at Google that's on the archive and will be at the NeurIPS workshop on deep inverse problems. Okay, so I'm interested. Imagine designing an airplane. There's a whole lot of complicated physics that goes into sort of how an airplane works, and sort of a huge number of engineering decisions. Going from things like how you design the engine to like sort of the shape, which is say designed for, I guess to get. Okay, I don't really know to sort of be maximally efficient. Sort of get there's sort of the shape of the wing. There's sort of all these sort of complex aerodynamics. There's sort of everything has to be sort of as strong as lightweight as possible. So lots of complex physics that goes into this. Obviously, airplanes are not designed entirely from first principles, but parts of them are. And I think if we had powerful enough computation and good enough optimization strategies, we probably would design closer to the entire airplane together. So that's kind of the simplest version of thinking about sort of physics-constrained optimization. One of the simplest problems here that I like to think about is a problem that's known as structural optimization, or sort of in the engineering literature, it's also called topology optimization. And here the idea is you have some structure, maybe you're designing a beam. You want to make the strongest possible beam that's sort of consistent with the laws of physics. And you're going to do it without any sort of prior constraints on the topology of your solution. So you're going to allow any number of holes here. And the question is, what is the optimal way to design this beam subject to the laws of physics? Here it's just the equations of linear elasticity. So pretty simple. We're going to say impose a force coming down from the top here, and we want to support it on two sides. And we do know the solution there's sort of an exact symmetry in the solution, so we'll only design half of it. But that's kind of our task, and this is kind of nice, a nice problem because you can it's relatively simple. You can find a MATLAB implementation, 88 lines of code. Of course, we had to rewrite this, but it's not too bad for trying things out. In terms of the constraints here, you have your physics here, which is just like your F equals ma for a bunch of springs, and then you have some constraints like for example, exactly 30% of these pixels are going to be should be filled in the final solution, and it should look binary. We need it to because that's either steel or air basically. So our inspiration for this work is coming from a really nice paper from a few years ago called the deep image prior. And so again, I'm going to show an example here for super resolution. So they use this for a lot of standard computer vision tasks. They call these untrained neural networks. I'm not sure I agree with calling them untrained, but I think they're very different. So I think it's some interesting ways. So let me give an example here. So instead of untrained, what they just optimize each neural network from scratch separately for each image. So no pre-training, no looking at like a large, looking at like pre-training on all of ImageNet, just like literally looking at an image. In this case, actually looking at like the coarse, crude image, like sort of on the coarse grid, and just looking at that, they're gonna optimize the neural net. So they're sort of with the strategy, what they can do is this is again bicubic sort of super resolution. Doesn't work terribly well, but their deep prior technique, sort of optimizing separately for each image, actually works pretty well. Almost in this case is almost as well as some of these fancy super resolution ResNet GAN methods. So this is pretty interesting. So I guess you ask, how can this method possibly work? So their hypothesis is it has something to do with this sort of the prior, that sort of the implicit prior that is sort of given to your solution by forcing the inputs to go through a deep neural network. So in their case, basically the model is you take a coarse image, you put it through some gigantic mega UNet thing, and then you try to ask it to say reconstruct the original image. And it turns out it is easier to reconstruct an image if you get like the fine resolution details right. It's harder to reconstruct things to reconstruct things with a coarse grid. Of course, if you train this eventually long enough, in this case, you train it for, 1 million time steps. Eventually, you get back. You're going to lose this detail. It's going to look like the coarse image you trained it with. But if you train it for some moderate number of time steps, maybe maybe 5,000 or 10,000 steps, you end up with a pretty good reconstruction. Just again, only like optimize on sort of one example. So we like that in the context of, say, these structural optimization problems, because it looks a lot like how those structural optimization problems work, in the sense that they're optimized on like a single example at a time. And we don't have to think about training a neural network for like an ensemble of tasks and this whole complicated supervised learning thing. We can just think about optimizing, say, a single example. So kind of the outline of how we try to do this is we're going to take a standard method for doing the structural optimization, which includes sort of a bunch of design constraints. It includes the physics here, which is just this solving for these the displacement from the forces, and some objective function here based on sort of minimizing the potential energy. And we're going to take the standard physics, which can all be made differentiable, and we're going to plug in a neural network that's going to generate the inputs. So basically, our generative neural network is going to start with a bunch of learned parameters that we're going to input into a dense layer and a bunch of convolutional layers that kind of make things bigger. And now we kind of make like a picture of a bridge, for example. And the picture of a bridge we're going to simulate, and then get some loss and sort of go back from this picture of a bridge all the way back into the parameters. So we're going to optimize the parameters of the neural network. And so instead of optimizing pixel values, we're going to optimize neural network parameters. And the hope is that by sort of forcing the model to go through this structure, it's going to be sort of easier. It's going to be sort of a better prior for the optimization process, because we know that there's some sorts of these designs look a bit like images. And again, we're going to do the whole thing together with automatic differentiation. So let me show you. So one sort of interesting point here that I think this is sort of aside, but I think this is kind of an interesting example of how to do these differentiable constraints. Is that to do this, we needed a way to construct. We needed some mapping that can give us take a bunch of real valued numbers and give us a bunch of numbers that are between 0 and 1. We know how to do that in machine learning. We can do something like a sigmoid transformation. That's pretty standard. But here we also need the sum of those numbers all to add up to some fixed constant too. So we also need the average of these numbers to add up. So that's maybe a little less obvious how you get like an average, how you get a bunch of numbers between 0 and 1 that add some fixed average. So I'll show you how we did it. And that is that we took kind of a standard sigmoid transformation, but we add sort of some global offset here in some sort of global bias. And we're this parameter b, and this parameter b we're going to determine implicitly via a search solution. So basically, we're gonna search for the right value of b such that with all these parameters, they all add up to the right fixed number, the right fixed total. And we can actually do that with any search procedure we like. Here we did it with a binary search, which is not differentiable. But it turns out you don't need to differentiate through your search procedure. That's not as, and you can actually just differentiate your constraints with these implicit derivatives. And so again, so we use this adjoint method to sort of differentiate through this. Okay, so I'll show you briefly the sort of thing we're trying to design here. So we kind of cooked up a bunch of, I guess we kind of got carried away and ended up with like 100 different example problems. They're not, most of these papers tend to look at like only a few examples. Maybe they don't have I guess some of these are a little contrived from the structural optimization perspective, but they're kind of, I think, interesting examples of sort of the, of what you can, like the sort of thing you can imagine designing here. So this is all 2D physics, it's all very toy, but basically we devise problems at sort of various different scales, ranging up to only a couple hundred pixels across, and designing things like here, this is like a bridge task here, where we're trying to span a canyon. Here, this is a beam task, we're trying to hold up some force pointing down over here. This is a ramp. This is a little contrived. This is just a hoop where I made a force down at every point on the outside. Okay, so we came with a bunch of examples like this, and then we benchmarked our techniques. And interestingly, it seems that this deep prior seems to help putting in this CNN structure. And I'll just show, particularly on our big problem. So about half our problems were on sort of these larger grids of at least 128 by 256 pixels. And on those problems, you see a gap. So here we're comparing these, the labels here. So here at the top is our method with the CNN prior. And then these red and green are two sort of standard baselines from the topology optimization literature. They're very, very popular. Down here is actually optimizing directly in pixel space, which turns out to not work terribly well because the way we handle constraints is a little unusual. It doesn't work as well as kind of the normal methods. And so this gap here is basically saying that this is a fraction of problems for which we had a significantly better solution. So it seems like on average we're at least for some fraction of these, maybe here is maybe a quarter of our design problems, we have a significantly closer to the optimal solution than these other methods. You can also look at this over an ensemble where you say like run it 100 times with random initial conditions and take the best one, and for there we also see a gap. Okay, so why are we better here? I guess I should say I don't think we really understand exactly why this works, but I'll show you some examples of what this looks like. This is designing this beam, and if you look at this over optimization steps, these losses go down. The top is our method. This is a fancy baseline. This is this sort of pixel space baseline. And you see that these very quickly you get like kind of a general structure. You learn the topology, and then it's kind of like minor refinements in the shapes of the beams. That's kind of what you see. These methods, this pixel space method gets kind of locked into a bad local minima really early, and then it gets stuck and like never ends up being very good at all. This is one of my favorites. Is that this multi-story building example where here is trying to support a force on each level. And you see that the CNN ends up with learning a solution that looks very qualitatively different from these baseline methods. This one looks like maybe a little more like a cathedral, but it's not a terribly good idea to span sort of giant spaces. That's not very strong. Instead, the sort of more organic behavior, sort of little cell-based system here is much stronger. okay, we can look at a bunch of, we looked at I guess we had, again, we had a bunch of these problems. If you look at this sort of in general, maybe what you can notice, maybe I think this beam is a nice example, it seems like perhaps our method is sort of picking out, is often ending up as sort of simpler designs. Maybe these are maybe these are closer to what, I don't know if there's an inherent reason why the simpler design is better, but at least by, these are better with our objective function. Maybe they're harder to find. You have to get like the simple design like just right. So that's sort of what you see here with like this beam example. If you look at, and oftentimes it ending up with something that's actually pretty different. So for example, this bridge here, it has only one support instead of two supports. So it's doing something interesting, perhaps. I'll just have maybe, I don't know, one more slide of sort of speculation on what may be going on. So this is, I don't know, if you look at a picture of, people like to visualize neural net loss landscapes. There's a nice paper from NeurIPS a few years ago on this. At least it makes some pretty pictures. Maybe we should try this for our technique. But there's kind of, we know that kind of how you parameterize functions makes a huge difference in terms of how easy they are to optimize. And this is this notion of some idea of preconditioning. So sort of transformations of your design space can make a big difference in terms of how an optimization process goes. So presumably our neural network may be doing something like that. There's kind of some hope perhaps that I guess we imagine that it may be sort of optimizing across multiple scales at once, maybe across sort of multiple sort of spatial locations. And again, it seems like empirically at least it's maybe a little biased towards simpler designs. And that's something that we can also kind of tweak if we can kind of tweak the biases of our model based on the architecture. So at least now we have some freedom to sort of explore a wide range of optimization strategies based on our neural net architecture. Okay. Okay, so almost done here. I'm going to give one last little pitch here for sort of a new project from Google that I'm really excited about. This is something I don't work on, but I'm just very excited about it, called JAX. It's kind of like TensorFlow or PyTorch, except it's really simple. It looks a lot like your code can look just like NumPy, except now you can run it. You get automatic differentiation. You can run it on accelerators like the GPUs and TPUs. And I think this is for sort of complex sorts of scientific computing, things like where you're not just like a standard supervised learning framework. I think JAX is really interesting. It's still relatively immature, but it's for doing sort of complex machine learning models or complex scientific machine learning models. I think it's an interesting tool to look at. Okay, so in conclusion, I think differential programming offers a new sort of exciting model for incrementally improving upon scientific computing without throwing away everything we know. And I showed you sort of two examples of how we can use this for improving PDE solvers or for PDE-constrained optimization.